and the floor is yours.
Hello everybody, good morning, good afternoon and good evening. On behalf of the IEEE Computational Intelligence Society and the IEEE CIS Task Force on Benchmarking, I am so excited to welcome Dr. Nikki van Stijn from Leiden University in the Netherlands. Nikki is Assistant Professor of Explainable AI and Evolutionary Computing at Leiden University and leads the Explainable AI Research Group within the Natural Computing Cluster. Her work unites evolutionary search, large language models, and transparent machine learning, yielding projects like BLADE and also LLaMEA, a large language guided evolutionary algorithm that designs optimization heuristics. We're going to hear more about those today. She's authored more than 90 peer-reviewed publications, is active in many industry projects, and promotes reproducible science, open source software, and interdisciplinary education. I am very delighted to welcome Nikki, and now the floor is yours.
Thank you for this wonderful introduction. Yes, I will tell you more about evolving metaheuristics, evolving algorithms by using large language models, and specifically the LLaMEA approach to this field of automated algorithm design. So this webinar was of course possible by the IEEE Computational Intelligence Society, but I would also like to specifically thank the Task Force on Benchmarking. Now let's start. So the core of this webinar will be about the approach introduced by us called LLaMEA and its extensions thereof. However, first I will give you an introduction of black box optimization and metaheuristics in general and what led us onto this road of automatic algorithm design. Then I will show you the core paradigms in automated algorithm discovery today and the many frameworks that have arisen over the few years. Then I will dive deeper into the LLaMEA approach, its hyperparameter optimization extension, and also a recent Bayesian optimization extension, its practical applications and already proven results on real-world applications, and then in general more about benchmarking these approaches and the reproducibility challenges that we have when we use large language models and also these evolutionary approaches. In the end, of course, there will be room for questions and answers, and I'm looking forward to a nice discussion. All right, first things first, an introduction into black box optimization and evolutionary computing, because this is what inspired us to actually start looking into automatic algorithm design. So when we have black box optimization, as the name suggests, we have some black box function of which we do not know any analytical structure. So we cannot easily calculate derivatives. We don't know what the structure of the objective function is, if there are any constraints. So it's really unexploitable. And this work like a black box makes it possible, of course, to query it, right? So that's the only thing we can basically do. We can give it some query x, and then we will observe some answer f of x. Some real-world examples, for example, you have some compiled legacy code, but you don't really have access of what is inside the library. So you can just fire the input as many times as you would like to do, and you get some result back, and in that way reverse engineer what the actual functions were, but you cannot look inside. Simulation models, for example, for car crashes, they're very complex, of course, that we don't have a mathematical closed formula of these, otherwise the simulations would not be required in first. So these are also considered black boxes. And also many different other kinds of real-life experiments, such as chemical reactions, etc. So just some visualization of some of these examples. In the bottom, you see a car crash where we can, for example, optimize the intrusion of the various components to make sure that the driver is kept safe. And here again, we have no clue what is the structure of this underlying function. We don't know exactly what are the constraints. Sometimes we have logical mechanistic constraints on the input space, but inside the simulator, the constraints might be unknown. Then when we have such optimization problems, the first and most relevant question to ask is how much does it actually cost to do such a function evaluation? So with cost here, we mean any measure of the resources we need to evaluate this function, usually convertible somehow to money, but this might also be a lot of time or a lot of computational resources. Where we can broadly distinguish cheap functions versus costly functions, and when we have a cheap to evaluate function, such as benchmarking functions in most of the time, we can do thousands of evaluations or even millions of evaluations without any problem. However, in real-world applications, the functions are usually quite costly, meaning we are limited to function evaluation budgets of around 100 to 200 max. Many algorithms work only based on these function evaluations, and these we call metaheuristics. These metaheuristics basically is a computational procedure that determines the most convenient way to find an optimal solution by iteratively trying to improve any candidate solution with respect to some measure of quality, the fitness function. But how do you know what kind of optimization algorithm is best for a given problem setting? That is a question that has been keeping this field of optimization busy for quite some decades now. One of the very successful approaches in this field is evolutionary computation and evolutionary learning, where we basically use the ideas from biology of surviving and reproducing to get more and more, better and better solutions by using the idea of natural selection. So something that works better than others will survive and mutate and recombine. And when we do this many, many times, we will end up with very good solutions. So how does that work in more concrete terms? Well, we start with some initial population of solutions, for example, by just sampling randomly. We evaluate these solutions. Then we select which of these solutions we would like to recombine. We recombine them in some form, for example, with 1 point crossover. Then we apply mutation to these solutions to introduce new variants. And we again evaluate the new offspring population. This offspring population is usually larger than the parent population, or at least equally large. And from this new offspring population, we select the best ones for the new parent population. And this process gets repeated till our evaluation budget runs out. The variation basically comes from this mutation and recombination. Environmental selection then can also take all parents into account. This is what we call elitism. And that makes sure that we will never lose any good solution. Now, in the field of black box optimization, we do a lot of benchmarking because we want to know not just is this algorithm performing good, but we would like to know on what kind of problems this algorithm is good. There is a no free lunch theorem in black box optimization, meaning that there is no universally best algorithm. It really depends on the type of problems that we are trying to solve. So while some algorithms might work on some kind of optimization problem, others will work better on other kinds of optimization problems. For this, over the years, there has been many tools and many benchmarking suites that were proposed, and they all have in common that they have different groups of benchmarking functions that try to represent different kinds of problems or of challenges that are often found in industry with black box optimization problems. These problems can look quite simple, like this sphere function, for example, into many dimensions, but can also have many local optima and very shallow and hard to find global optima. Now, how does this connect to large language models? Well, large language models in the beginning, so in 2023, when a paper started to appear on large language model in combination with black box optimization, the first uses were quite relatively simple. For example, large language models were just, or actually evolutionary computation was used to optimize the prompts of large language models for certain tasks. Also, large language models were used as recommenders for setting hyperparameters of evolutionary algorithms, for a specific task. It has also been shown that we can even use LLMs to act as the optimizer by allowing it to sample or to give basically a hint of where to sample the next points. And only recently LLMs are also used to really design complete algorithmic components or even complete algorithms. So that brings us to the core paradigm of automated algorithm discovery. In 2024, Oliver Kramer came there with the work Large Language Model for Tuning Evolution Strategies. And this was one of the first works where large language models were actually used to set the hyperparameters of some evolutionary strategy for a specific class of problems. And there they showed that already for using basically hyperparameter optimization, LLMs seem to be useful because large language models can actually exploit information they already know about certain tasks. So if you already have an idea of the type of problem that you are working with, this can help you to basically navigate the very large, complex landscape of optimization algorithms and their hyperparameters. Another work used large language models actually as evolution strategy, where the LLM is proposing where new solutions should be sampled. Now, while that is quite interesting, the general idea behind LLM-EC for algorithm design, so really designing the entire algorithm, is that we have some problem specification, then an LLM that generates some code, some candidate algorithms, and these candidate algorithms get evaluated, for example, on some benchmarking functions. Then this evaluation provides the evolutionary loop with which candidate algorithms should be kept inside the population and how they should be mutated by the large language model. These candidate algorithms are then fed back to the LLM together with their benchmark performance data, and the LLM is queried to basically mutate these code bases. One of the earliest works that basically introduced this concept was from Google DeepMind, FunSearch. FunSearch basically used a code specification with a placeholder of what part of the code should be changed. So take note that this is basically only changing a small portion of code, so like maybe 10 lines, and then asking a pre-trained large language model to fill in that piece of code many, many times. They used roughly 4.5 million of these LLM evaluations or calls, and then evaluated the adapted code on their problem specifications. Each of these programs was then stored in a database, and this database was queried to get the top K, for example, and insert that into the next prompt, etc. They showed that that already reduced quite some novel ideas, and also that these algorithms could outperform human-designed ones. Evolution of heuristics took it a small step further and basically proposed to not only evolve the code, but also a natural language summary of the code that they are calling TOTS. Again, this procedure is in principle used for generating small heuristics that are, for example, then implemented into guided local search. EO8 focuses on combinatorial optimization problems such as online bin packing and traveling sales person problems, because that's what they are doing most in that group. And they've shown that that works much more efficient than the previous fun search by using an evolutionary loop. After EOH came ReEvo, which is as a similar overall loop as evolution of heuristics, but also includes a reflection step where the LLM is basically being asked to reflect on its performance and on its ideas of mutation and adaptation of the code, both for short-term reflection and also a long-term reflection, and that guides the search into regions that are hopefully interesting to explore. It's mainly used to improve existing algorithms, and again, for as similar as EOH, this works on relatively small code bases. Our approach, LLaMEA, we introduced in 2024 in the IEEE Transactions on Evolutionary Computation. And while we were aware of EOH and fun search, we had a slightly different angle, as we first of all came from the black box real optimization domain. So we are not working with integers or booleans, but usually with real numbers. And furthermore, we wanted to first understand one, how does evolution work in such a loop? So what are good evolution strategies? And also, can we generate a complete meta-heuristic algorithm instead of just a code snippet that is living inside a larger framework? So with LLaMEA, we showed that we can synthesize complete black box optimization algorithms. It did require that we are very careful with loading and checking the algorithms that are being generated. So we also include a self-debugging feature, where basically whenever an error is introduced in the code, we can feed back the stack trace to the LLM in order for it to try again and resolve the issue. I will go into more detail a little bit later, but finally, I would also like to introduce or to show AlphaEvolve. AlphaEvolve also came from Google DeepMind. It was their answer on their previous fun search. And AlphaEvolve is also, like LLaMEA, an algorithm that can produce complete algorithms, not just for black box optimization per se, but they focus on general purpose algorithms, which can be a lot of different applications. Unfortunately, it's not open source and is also therefore not reproducible, but they, in their paper, they do show a lot of interesting applications. Now to dive deep into LLaMEA, an LLM evolutionary algorithm. So the overall LLaMEA framework is still following this evolutionary loop of problem specification, LLM code generation, evaluating candidate algorithms, selecting the candidates for the next iteration, and then prompting, for example, with mutation prompts to refine and redesign the different candidate algorithms inside the loop. In addition, we also have an optional hyperparameter optimization, which does not happen inside the LLM, but inside the evaluation. So in more detail, we synthesize the algorithm. We then load this Python algorithm into a safe virtual environment. We check if the code contains any errors, such as libraries that are not installed, or just syntax errors. And once it is error-free, we evaluate it using our extensive benchmarking tool IOH Experimenter to gather anytime performance statistics. These performance statistics are then stored in the session history for each of these synthesized algorithms. We pick the most interesting, so the best anytime performing algorithms for the next iteration, and we ask the LLM with multiple different prompts to redesign or refine the selected algorithm. In pseudocode, that looks like this, and when we introduced LLaMEA, we wanted to start as simple as possible, meaning we started with a 1+1 evolutionary strategy. In other words, we have one parent that generates every iteration exactly one offspring. Why did we do that? First of all, it's known that a 1+1 evolutionary strategy is very sample efficient, because every iteration we have the chance to improve, and we only accept a new solution when it improves over the older one. Now, normally, a 1+1 ES could get stuck in a local optima. However, with LLMs, there is a lot of degrees of freedom in the search space, because the code search space, well, the dimensionality is huge. So the chance that you get stuck by using an LLM to sample new algorithms is relatively low. So what happens? Well, we ask the LLM to sample our initial generated parent program, and we then do this loop where we usually set t to 100, meaning we only generate 100 different algorithms, and we only evaluate, of course, these 100 different algorithms. Then we use IOH Experimenter and IOH Profiler, some benchmarking libraries, to actually get the fitness values, any feedback, any error feedback, and perhaps more detailed feedback from the benchmarking suite. All this feedback is then being fed back into the LLM to generate the next offspring algorithm by mutation. This offspring algorithm is again evaluated. If the offspring algorithm is better than the parent, it gets selected as a new parent, and otherwise we just stick with the old parent and perform the operations again. The part that is still quite manual in many of these automatic algorithm design frameworks is actually what prompt do we use. So first of all, we have a detailed task prompt where we basically instruct the LLM what task it is solving. Here we should of course be careful that we do not leak any details about the task itself that could bias its results. So we keep it relatively simple. It should optimize some black box function. It should write optimization algorithm in Python code, and the code should contain certain functions with certain signatures, so that we can easily extract it and apply it. And it should adhere to some output structure. Then inside the loop, we also have the feedback prompt, which basically lists the best parent program at the moment, and then simply the words either refine or redesign to improve the algorithm. Now this last sentence can of course have quite some influence, so we tried in the past many different mutation prompts and also tried to optimize these on the fly. So how does it actually work? So the very first iteration of LLaMEA on black box optimization, we did a big experimental setup of 24 black box optimization functions from the Bebop suite, with each having 3 different instances, where an instance is basically a translation or a rotation of the function, so that we do not know where the optimum is. and 3 runs per instance with different random seeds. Then, as quite common in this field, we used 2000 times the number of dimensions, so in this case 10,000 function evaluations, and we initially did it for a dimensionality of 5. We set t to 100, meaning we only evaluate 100 of these algorithms, and the performance measure was an anytime performance measure, which you can roughly describe as the area under the curve, or in this case the area over the convergence curve, which we can aggregate over all the functions and over all the different runs. So the results, well, we probably would not have published this if we were not one of the better ones, but we also found out that LLaMEA with a 1+4 elitism, and in that case with GPT-4 Turbo, was performing the best. And there were quite some differences depending on what large language model we used. Now, just for as a note, the 1,1 strategy is basically just random search, because we do not keep the best of the two in each loop. So this was more of a check, a sanity check. Also, when we would compare this with evolution of heuristics, for example, with the same LLM and also just pure random search, then we can see a clear performance improvement. Now, what we were also very much interested in was not just the quality of the generated algorithms, but what the LLM is actually coming up with. So here we see a word cloud, for example, of all the different algorithm names it had invented among the different runs. In total, we generated roughly 5,000 different algorithms over all these different runs. And just to give you some examples, some of these names were very descriptive, like surrogate-assisted differential evolution combined with covariance matrix adaptation evolution strategies, which basically in one sentence says exactly what it should be. And also upon inspecting of the code, we saw that this name was roughly correct. Sometimes it introduces words we would probably not prefer to see that much, like dynamic firework optimizer or quantum flux ultra refined. Well, it has nothing to do with quantum or with flux, but the LLM, of course, learned from a large body of algorithms in the literature, and some of the more fancy ones do indeed have this kind of names. We also looked at how the LLM was actually mutating or redesigning the code among the different iterations. So for example, we looked at code difference ratios, so the number of lines of code that are different between the parent and the offspring, then divided by the length of the largest code, and calculated for each of these runs between the parent and the offspring this difference. So when we look at these differences, we can see some interesting trends. For example, the mutation rate, so to say, the lines of code that got changed for GPT-4o is much smaller than the average mutation rate of GPT-4, which basically shows that GPT-4, at that time at least, was exploring more than GPT-4o was. But how does this actually compare to human-designed algorithms and also optimized human-designed algorithms? So for that, we basically evaluated some of the best generated algorithms, like this quantum flux ultra refined algorithm, with different human baselines, of which the strongest baseline was a CMA-ES algorithm, but then optimized with over 50,000 different configurations, optimized for the best AOCC on exactly the same benchmark. So this is a very hard benchmark to beat, but the best generated algorithm did, at least in terms of AOCC and also in the terms of the end result, beat this optimized CMA. As slightly weaker but still competitive baselines, we also just show the performance on a standard CMA-ES and a standard differential evolution. This ERADS quantum flux ultra refined algorithm is basically a kind of differential evolution. That's why it makes sense to also compare it with a Bayes differential evolution. And here we see that it very much outperforms these. It's also interesting to see that some of the other algorithms that got generated, while not having the best AOCC over the complete budget, it does show very competitive performance for smaller budgets. The best algorithm that we generated in this study, we also submitted to a competition in Gecko 2024, and there we won the first prize. So that also shows that, again, we were able to beat human designed algorithms, specifically for certain benchmarks. This benchmarking competition was not done on the BBOB benchmark, so it was not actually in our training data, but it was on a many affine version of that benchmark. So then we look deeper. How does the LLM actually do mutation? So we looked, for example, at code differences between the parents and the offspring, and roughly speaking, we saw 3 types of mutations happening, sometimes together, sometimes separately. What we saw that, of course, sometimes new code, new structures get introduced. This is, I believe, the most interesting thing to happen. This is what you want. You want the LLM to search in different algorithm structures that have been unexplored yet in the literature. Other times it just updates comments to explain the mutation it is performing. So while we do measure them, for example, when we look at code differences, they are not really that interesting in algorithmic perspective. They are, however, interesting from an explainable perspective, at least if we can show that these comments also make sense. And the third thing we saw was that it basically tries to perform hyperparameter optimization of the parameters it introduced itself. So it changes, for example, in this case, the F and CR value, which are 2 very common differential evolution parameters, in order to optimize this algorithm. So then we thought, okay, if an LLM is doing hyperparameter optimization, just changing numerical values of its generated algorithm, that does not make a lot of sense. Large language models are not that good in numbers. We all know that. So why don't we merge these 2 things together? Why don't we just use LLMs to really focus on the structural part of the code and use hyperparameter optimizers that exist for quite some time, or in-the-loop hyperparameter optimization? And that's exactly what we did next. So instead of asking the large language model to synthesize the algorithm, we also asked the large language model to synthesize a configuration space of the algorithm and to expose all the parameters that the LLM thinks are interesting to optimize in the algorithm header. So now we still provide the same problem specification and an example code with an optional configuration space. The LLM is then synthesizing new algorithms and synthesizing new configuration spaces, which we need to extract. Sometimes these configuration spaces, which are basically Python dictionaries, can be complex, can contain faults, can contain parameters that the actual algorithm does not have, for example. So we also need to do additional error checking on the pair of algorithm and configuration space. But in many cases, the LLM gets it right, and we can extract both the algorithm and the configuration space and apply a hyperparameter optimizer inside the loop of algorithm design. In this case, we used the quite famous approach called SMAC, which is a sequential approach to doing hyperparameter optimization. And SMAC can also utilize different instances to basically speed up the optimization process. So we don't need to do the full benchmarking suite for every combination or for every hyperparameter configuration, but we run a few instances at a time for each configuration, and in that way determine which configuration is likely best. So we don't lose that much time, but we do win a lot of efficiency on the large language model side. So when we look, for example, at the BBOB problems, we see that with just around 20 LLM prompts, we can get to the same level of AOCC, so the same goodness of the algorithm, as what we can get with LLaMEA in roughly double that number of LLM prompts, and for EOH it takes even longer. Now that does mean that we need additional benchmark evaluations, so it does take a bit more compute. So for the new approach for LLaMEA HBO, for this 100 LLM prompts, so these 100 algorithms, we did use 9 complete benchmark evaluations per algorithm to tune its parameters, meaning in total 900 benchmark evaluations. We also then let EOH run much longer, namely for 900 iterations, so 900 algorithms, just to do a fair comparison. So how does this translate to other problem types? I've shown you a lot on black box optimization benchmarking. That might not be your field. You might wonder, how does this approach actually transfer to other problems? So first of all, does it generalize to other optimization approaches like combinatorial optimization? Well, yes. Actually, it should generalize roughly to any kind of problem that you can automatically assess the quality of the algorithm in at least a little bit sensible time. So for online bin packing, we compared again with EOH, which was by that time the state of the art. And we show that with this hyperparameter optimization inside the loop, with just a budget of 100 LLM prompts, we can easily beat the previous approaches. We do see that in this case, in one run, the original LLaMEA even got a better result, but yeah, that's just being lucky. For the traveling salesperson results, that's even more obvious. So here it shows that we basically have a 0% gap in this case. So we basically solved the problems that are in the training instances. And this also made us think, because this seemed a bit too good to be true. So what's actually the case, and we took these benchmarking suites from the FunSearch and EOH papers, that these TSP instances that were used during training of this LLM approach were quite simple, actually. So what did we do? We tested the best heuristics found by each of these approaches on a much larger scale of problems using the TSP-lib Euclidean problems, which is a really large library of TSP problems. Well, more than 100 different ones of various sizes, with also large instances that do take quite some compute to approximate. And here we show that basically the algorithms that LLaMEA HBO found already in the second iteration, or already after, well, way less LLM calls than EOH, we get similar performance. So all of these different heuristics were not that much different in the end on real-world problems. That also made us worry a bit about this whole field, because apparently we really need some stronger and also better benchmarking to say something that is really valid for these generated algorithms. So we should really carefully think, what problems do we put inside the loop of this algorithm design methods, and what do we put after that? So what do we test on, and what baselines do we use for the evaluation? The next part is a little bit different, namely the automatic design of Bayesian optimizers. And why is that different? Well, while we could just use LLaMEA out of the box for Bayesian optimization, there are some challenges with these optimizers that make it harder for LLMs to actually evolve them. So first of all, Bayesian optimization uses Bayesian inference to get an idea of the objective function. So in Bayesian optimization, we have a machine learning model, usually a Gaussian process regression model, to fit the objective function in some way. So when we have some observed data, so we have evaluated our real objective function a couple of times, we can start fitting such a model. And these models don't only give you a predicted mean, but also a predicted variance or confidence. And this confidence can be exploited, and that is exactly what is being done in Bayesian optimization. And this exploiting of the confidence and the mean of this predictive model is done with a so-called acquisition function. This acquisition function gives a high value when it is likely that a point will actually improve over the so far best found point in the observed data. So we optimize this acquisition function to basically find the next point that we want to sample. When we sample it, we can then also update our machine learning model and get a better sense of how the objective function really looks like. This is quite an iterative approach with the following modules, namely we have an initial sample, we do the model fitting, we have an acquisition function that we optimize, and then we repeat. So what is the difference between LLaMEA and LLaMEA BO? Well, first of all, since BO algorithms have such a very standard framework, we also start with a prompt example where this framework is explicitly mentioned. In addition, we apply a new prompting idea where we really promote diversity in the initial population. So we provide the LLM with the population that we generated till now and explicitly ask it to give us something new. Another difference with the default LLaMEA is that we now have lambda parent algorithms and mu offspring candidate algorithms. So this looks more like a basic evolutionary strategy with larger population. So as I said, we use slightly different prompts than in the original LLaMEA, and that's just to promote this diversity. Because in the end, we don't want to start with a population that contains all the same kind of algorithms, because that really reduces our chance to find the best one. Then the mutation prompt stays roughly the same, and we also introduce a crossover prompt where we simply ask the LLM to combine two parents into a new solution. Again, we train this approach on BBOB 5D, but with a lot smaller evaluation budget, as we now assume that the evaluations are costly, meaning we can only have a few hundred as our budget. Now in this approach, we also looked very closely what kind of algorithms is it actually trying to explore. Is it biased towards one family of algorithms? Is it exploring between different kinds of algorithms? And what in the end works? So what we see that in the beginning, it was trying really standard stuff like Sobel sampling, LHS sampling, partition search, multi-fidelity approach, some upper confidence bound acquisition function, some expected improvement acquisition function, etc. But then it became more and more sophisticated. It started to do some k-means sampling, which I've not seen before, and then it switched to trust regions. Trust regions in Bayesian optimization are by now quite known and very effective, because it basically shrinks the area in which we are searching and in which we are training our machine learning model, which really makes it computationally much more efficient. So the best algorithm that it came up with is called ATRBO, and let's just have a little bit of a look at the code. So here, this method that was introduced by the LLM at a later stage of the optimization uses trust regions implicitly by uniform sampling, but is also updating this in a hypersphere. And this sampling within a hypersphere is quite interesting because I've not seen any algorithm doing that so far. Of course, I'm not aware of all the algorithms that are out there, but we searched quite thoroughly and we could not find anything that did this. But it does make sense, especially on the BBOB functions, because many of these functions are spherical. What it also does is has an exploration-exploitation trade-off by an acquisition function that's being adjusted each iteration. That of course makes a lot of sense. Now, how did these algorithms generalize to different dimensions of the problem? Surprisingly well. So we can see that even when the dimensionality of the problem grew to quite high, to like 40, in this case TR-evil, which was a different generated algorithm, performed the best, but also ATRBO was still on par with the state-of-the-art human-designed algorithms, which you can see in blue. So in blue we have CMA-ES, which is not a Bayesian optimizer, but just there for reference as a good general optimizer. HEBO, Turbo 1 and Vanilla, of which HEBO is the best state-of-the-art Bayesian optimizer that we have so far. Now we can see that basically ATRBO was the best and also statistically the best BO algorithm over the human baselines on the lower dimensions, and TR-evil was the best generated BO algorithm and also beating the human state-of-the-art in the highest dimensions. Now, how did these algorithms then generalize to other problems that they were actually not trained for? For example, how do these work in AutoML problems, which is a completely different kind of task, but also usually solved with Bayesian optimizers? So here we evaluated the 4 different generated algorithms on the BaseMark AutoML benchmark, and well, we did quite nice. We didn't win everywhere. There we also compared to an algorithm called Lambo, which uses an LLM inside the Bayesian optimization loop, and Lambo won for the decision tree and for the random forest cases. But when optimizing other models like AdaBoost, MLP, and SVM, we did surprisingly well. While the LLM has never seen these problems, of course, and also the algorithms were not really tuned for this task. We did, in addition, some CPU time analysis. So our main competitor in that task was an algorithm called Lambo, where the BO was actually using the LLM as operator. And because it uses this LLM, this Lambo approach takes quite a lot of time and also a lot of resources if you're not using third-party APIs. So it takes 10 to 100 times longer, and in addition requires these LLM API calls for each of the evaluations. And the generated algorithms were basically as fast as Turbo 1, meaning we can basically get solutions within 0.2, 0.3 seconds. All right, I've shown you a lot of benchmarking experiments, but how does this approach actually work in the real world? To start, we did a benchmarking task on a real world problem, namely the optimization of photonic structures. So photonic structures in this case are just layers of material stacked on top of each other And the task here is to define the thicknesses of the material in order to optimize some specific value. In this case, uh, the photovoltaic resistance. So what did we do? We applied LLaMEA on this problem, where we trained on a problem with a number of layers of this material that was much smaller than the original problem. So we basically created, or we used, a mini version of this real-world problem called mini-brag that we used inside the LLM algorithm design loop. We found a couple of algorithms that performed really well, denoted here by first best, second best, and third best. And then we applied these algorithms without any modification on the larger instances, on the brag, which is much more complicated to, uh, to minimize. And what we found is that these three generated algorithms actually performed perfectly. They were clearly beating the state of the art, and which were all specifically human-designed algorithms that were made by in 2024 specifically for this problem. So this showed that basically with LLaMEA, with automatic algorithm design, we could beat some very clever human algorithm designers. In addition, and this is not yet out there, so it's under review, but it will be on archive in a couple of days. We have a GPU auto-tuning methodology where we applied and we actually changed LLaMEA to work for kernel tuning optimizers. So we can develop automatically optimizers with some specific target application, and by giving it additional information about the kernel search space, which is commonly known in this kind of applications, we could show that we can really improve the algorithm performance that we got when generating these algorithms. The discovered algorithms were on average 50% better than the state of the art for 6 different GPUs and 4 different kernel applications. So that's quite a win. And in this case, it's very important that these algorithms perform under a set budget of time. So the CPU time or the walk clock time here is much more important than the number of evaluations, which also shows that quite often real-world applications have different constraints than benchmarking applications. The works that we have evolved so far were lucky or were good enough to win a couple of competitions. So we have won the anytime algorithms for many affine bebop functions in Gecko, both in 2024 and also this year in 2025. Also at Gecko, we won the UMIS Award for a solution that uses evolutionary algorithms to compete against humans. And last but maybe not least, at least for me that was a lot of fun, we participated in the IEEE Conference of Games, where we competed in the Planet Wars real-time strategy competition and got the third prize by the agent that was actually evolved by our LLaMEA approach. Now this agent was only using Metaheuristics, and the winner one of the winners of this competition used reinforcement learning a little bit like AlphaZero. So that's, of course, yeah, well, that was a lot more effort that they could put in. But it shows that even with just meta-heuristics, you can get quite far also with doing this kind of game agent design. All right, so it works quite well with the real world. We can show some competitive results on benchmarking problems, but we've also seen along the way some concerns or some issues with this benchmarking. And that gave us the idea to basically set up some standards and some benchmarking tooling to guide the field into the right direction. So LLMs now design optimization heuristics and complete algorithms automatically, but this is a very opaque generation process, right? We don't know exactly what's being generated unless we look carefully at each and every one of them. We also don't usually know everything that is in the state of the art. So how do we make sure that LLMs come up with something novel, for example? There are a million ways to code the same algorithm in many different ways, right? While it still performs roughly the same, or it still has the same ideas. Also, it's very hard to reproduce these results. LLMs by themselves have quite some stochasticity, and not all the platforms allow for easy reproducibility. It would also be much better if we have a capability-oriented evaluation platform, not just where we want to see what works the best, but also where we can analyze what kind of capabilities does this approach have. Can it explore well? Can it find novel solutions? Can it find can it exploit very existing solutions well, for example, etc. And existing literature, such as FunSearch, EOAs, but also others, have shown over the years quite several limitations, basically. For example, there can be too simple problems that then do not really generalize to other instances. There can be different variations due just to prompting. So the prompt is a very important part in all of these processes. The variations can also be just due to different LLM versions. If you have even the same LLM, but it just got updated by the vendor, then you might suddenly be better than the competition, but it has nothing to do with your algorithm. It's just the LLM getting better. It can have reproducibility issues due to incomplete logging. So for example, not everything gets logged for every paper. FunSearch, for example, only shows the final evaluations that they performed. And quite often there's no statistical analysis, so only one or maybe 3 runs are provided. That has a very clear reason, namely the costs are usually quite high, but still it's something to keep in mind. And also the validation of the final results is just as important as evaluating the overall methodology. So the final algorithms that it comes up with, what are the baselines we should validate against, and how can we standardize this? To at least start tackling this bunch of problems, we started a project called Blade, which you can easily install with pip, and then it's called IOH Blade because Blade was already taken. But an IOH stands for iterative optimization heuristics. But basically Blade builds on already existing evolutionary computation benchmarking best practices. So we initially really focus on black box optimizer discovery. It supports almost all of the LLMs with different connectors, and it also integrated with the already existing IOH benchmarking tools for black box optimization, meaning it has many different problems that we can easily just pull in. And it evaluates the code in a safe virtual environment where we can use different dependencies per problem. In addition, we provide already several baselines that are programmed with the same interface. So we have evolution of heuristics, we have re-evo, we have LLaMEA, and we also plan to implement FunSearch, or at least something that should work similarly to FunSearch. And it can be easily extended for your own algorithm. The benchmark that it currently provides are the black box optimization benchmark of 24 noiseless functions, but also the boundary constraint functions, the many affine combinations, and some real-world examples, such as the photonic structure optimization problem, and we are rapidly extending this benchmark sets. But keeping in mind that each of these benchmark sets should have some capability-focused idea behind it. So we don't just benchmark problems to benchmark problems. We really want to start to understand how different methods, how different evolutionary methods, how different prompting methods, how different LLMs affect the performance on certain kinds of problems. So there we look at generalization across instances or across dimensionality. We look at different problem class specialization. So how much information, for example, can you inject into the prompt to better exploit certain problem classes, where we of course train on different instances and then test the final algorithms on unseen instances. Basically, we are building a tool for LLM evolutionary computation inside the explainable benchmarking area. So the overall workflow is we define, we run, we log, we analyze, and we compare. I do think we are almost over time, so let's conclude here. LLaMEA can effectively find strong algorithms that sometimes surpass state-of-the-art. Basically, interpretation is that LLMs are a kind of universal modeler framework for algorithms, and by sampling these, we can basically find the best algorithm instantiation for a specific set of problems. In-the-loop hyperparameter optimizer reduces the LLM calls that are required to get these good solutions, and we can also do this for Bayesian optimization. Future work includes using multiple LLMs in the same run to basically enhance their strengths and weaknesses, and controlling the diversity of the algorithms we generate. Co-evolution of the prompts and operators seems also very interesting, because that basically would, on the long run, with longer evaluation budgets, perform even better for algorithm design. Thank you very much, and I'm looking forward to your questions, and you can contact me anytime also after. Thank you.
Thank you so much for that talk, and I'm really impressed by Blade as well. That's something that I'm pretty sure many people on here will want to actually experiment with. Now, I know we're slightly over, but I do feel that we should have at least one question. So Roberto has asked, what is the possible growth rate for this strategy? And this was around about 237. So basically, I'll read the whole question. And how much computing time will be required for the readjustment? Do you think this strategy could be used to create an updated meta-heuristic for each person in a country? So it was quite a few slides ago, but are you okay answering that question, or?
I'm not sure if I understood it completely correct, but I think the question refers to how does it scale, right? So how computationally expensive is all of this? So basically, generating or evolving these meta-heuristics does not take that long. It depends, of course, on the problem that we are creating them for. In the case of benchmarking, where evaluation only takes a couple of milliseconds, we can do a whole run of 100 algorithms in a single day quite easily. We can also parallelize that, so we could probably scale it down to around an hour for a whole evolutionary loop. If you have a real world problem that is quite expensive to evaluate, then it can really become slow, right? In the end, we do generate at least 100 algorithms. Sometimes for harder problems, we could even scale that up to 1,000 algorithms. And then it might take, I don't know, a month or something. So this should really be used for problems that are occurring over and over again, like optimizing car shapes or doing crashworthiness tests on structures. These are very expensive, but they need to occur every time you make a modification to the car design. So this is really worthwhile to get the best algorithm for, because once you have a better algorithm, you save a lot of time in the long run. So that's the kind of problems that we try to tackle. I hope that answered the question a bit.
Thank you. There's quite a few now, but I'm just going to do one more because we are over. And this one says, beyond comparing an algorithm with other existing algorithms, how do we determine whether a specific AOCC value is acceptable? Is there a well-established threshold in the literature that allows us to determine that our AOCC is sufficiently good, or is it truly problem specific?
Yeah, that's an excellent question. So that requires a little bit of background. So the AOCC, so the area over the convergence curve, is calculated using an upper and a lower bound. So we should know the optimum of the function to calculate this thing correctly. And then it depends a bit on your budget on how to set this realistically. So for black box optimization, without using Bayesian optimization, so with a large budget basically, an AUCC around 0.8 is very good. But if you have only a very limited budget in black box optimization, for example, then an AOCC of 0.2 can still be really good. So it's really dependent on the problem and on the budget that you allow the algorithm to use. There are, of course, other metrics like final fitness value that is looked a lot on, and that's completely problem dependent. But then when you know what good fitness values are, it's easier for an expert, for example, to understand what is good and what is bad.
Okay, thank you so much. As said, we are over, so I'm going to have to end the webinar now, but I would like to do two things. If you've got any specific questions, I'm really sorry we couldn't cover all of them, please reach out to Dr. Nikki Van Stein in advance. You will have seen her details, so please reach out. And all this does is say a massive thank you to everyone for attending, an even bigger thank you to Nikki for that really outstanding presentation. Thank you so much, everyone, and we will see you soon. Thank you. And I think, Joellen, are you going to put